If you look at part A on your worksheet, we're simplifying square roots and third roots and fourth roots. What is the square root of 36? 6. That's not bad. Square root of 24? It's going to be a decimal. Without plugging it into your calculator, what would we expect it to be? Close to 5. How come, Derek? The square root of 25 is 5, and 24 is just slightly below, so it's probably 4.8 or 4.9. The decimal equivalent, or the decimal estimation of this, is not as valuable as the simplified version. So supposedly you learned this before. This is just review. Do you remember how to simplify square roots? Factor it. We want its prime factorization. 4 and 6, 2 and 2, 2 and 3. So 24 is made up of 2 times 2 times 2 times 3. Is there any other way to create 24 using prime numbers? That's it. There is only one way to write any number using prime numbers. Okay, it's called the prime factorization. So once I have it factored, what do I need to do? Well, some parts of this are going to remain inside the square root, and some parts are going to come out. What should we take out and what should we leave in? We're going to take some 2's. Austin, did you have your hand up? No. Anybody remember how to do this? Right, we're looking for pairs, not the fruit, but 2 of a kind. So we have a pair of 2's. And for every pair, we bring one number out. So those 2, that set of 2 is eliminated, and on the outside of the root, we write a 2. Now the 2 and the 3 remain, so what does that give me? Do I add them or multiply them? Multiply. Everything today is going to be multiply. So 2 square roots of 6. Well, who thinks that looks more complicated than the square root of 24? Why do we do this? For the same reason as this. If I gave a problem and people came up with different answers, and those were the answers that were spread around the room, who's correct? They're all the same, but we don't prefer any of those numbers. What do we prefer? 1/2. And we prefer it for 2 reasons. First, if everybody simplifies their fraction, they'll get the same answer. And that's important. There are many ways to write square roots, some of them. Root 24 can only be written, well, it can be written in a lot of ways, but not as many as some of the others. And if everybody simplifies their arithmetic down to the bottom, everybody will get the exact same root, because there are many versions of some of these. The other reason is, if you simplify square roots, you can sometimes combine them. I'll give you an example. The square root of 12 plus the square root of 27. We cannot add those together. They're not like terms. In order to add square roots, the number under the square root has to be the same. So you could add the square root of 3 to the square root of 3, or 4 square root of 3 to the square root of 3. But if we factor these out, 4 and 3, 3 and 9, 2 and 2, 3 and 3. Here I have a pair of 2's, and here I have a pair of 3's. So 2 square root of 3 is equivalent to root 12, plus 3 square root of 3 is equivalent to root 27. And now all of a sudden these have the same roots, so the answer is 5 root 3. So that's another reason why we simplify them down, because sometimes it will allow us to combine roots. Okay? So my next question is, what's really going on here? What allowed us to bring a 2 out? Why did we pull out a pair of numbers? You might not know the answer to this one. Okay, what do you mean by balanced? How how does root 24 balance with 2 root 6? Because that's a good way to look at it. Yeah, I'll answer that in a second. Let's look at the next one. Let's review really quickly. How do you know if a number is divisible by 2? It's even. That's easy. So 2 goes into 216. How do you know if a number is divisible by 3? Something, you add all the digits together, and if it equals a number that is divisible by 3, then the whole number is divisible by 3. What if I add all the digits together and I get 4,821? Add the digits together again, and if I get a big number, add them again. And you can keep adding the digits together until it reaches a number small enough that you can tell if it's divisible by 3. One time I saw an explanation of why that's the case, and I understood it when I looked at it, and then I forgot it. So I don't know why, but neither does anybody else. How do you tell if a number is divisible by 4? Good. 4 goes into 100, which means it goes into 200 and 300 and any multiple of 100. So if I look at a number and I erase the last 2 digits, turn that into a 200, then 4 would work. So if I erase the last 2 digits here and made them zeros, 4 goes into 1200. So you just have to ask, does 4 go into the last 2 digits? In part C, 4 goes into 16. It's not going to go into E. Is it going to go into F? Yeah, 4 goes into 32, so it goes into 432, and it doesn't go into G. 5 is easy. How do you tell if a number is divisible by 5? It ends in a 5 or a 0. How about 6? Right. If the rule for 2 and the rule for 3 works, then 6 works. 7 has a crazy rule that I just learned today, which is if you double the last 2 digits and add that to the rest, and you get either 0 or a number divisible by 7, then it is divisible by 7. My recommendation is, if you think it's a 7, just divide it and try it. Because that rule seemed like it would take way more time than to just try 7. 8 and 9 don't have any rules. 10 if it ends in a 0. 11 doesn't have a rule, but 12 does. If rule 4 and rule 3 work, then rule 12 will work. And then after that, there are some other rules, but we won't go into them. So I know 2 goes in here, I know 3 goes in here, I know 4 goes in here, so I know 12 goes in. 12 and, help me out somebody. 12 and 18. So 6 and 2, 9 and 3, 2 and 3, 3 and 3. And I'm looking for pairs. Do I have any pairs? I have a pair of 3s. Did I not do something right? 3 and 6. Sorry, guys. 6 and 3, 2 and 3. Okay. Pair of 3s and a pair of 2s. So what do I write on the outside? 6. Now looking at the variables, can I remove any x's? I need a pair of x's to take it out, and I only have one, so the x is going to stay on the inside. Can I remove any y's? Y to the fourth has how many pairs? 2 pairs with how many left over? None. So y squared. How many pairs of z's can I remove? 3 pairs with how many left over? So z to the third. Square root of, what number did I have left? I had a 3 and a 2 left over. So 6. Any x's remain? An x, any y's? All of the y's came out. Any z's? I brought 6 of those z's out, 2 or 3 pairs of z's. No, 3 pairs of z's. 6xz. Now, what if it was negative 216? How would that change the problem? It would create an I. Whenever you have a negative inside a square root, you get an I. Where do we place that I? It's got to come out of the parentheses, but it needs to be behind the variables. So the I is always the last thing in front of the square root, if it needs an I, but this one doesn't. So I'm going to take it away. So, what's really going on here? Why are we allowed to simplify some of them and not simplify others? How come we're taking 2 things out at a time? The reason is this is a square root. You're asking what times itself equals the given number. So if I were to list all of the perfect squares, 1, 4, 9, 16, 25, help me out, 36, 49, 64, where am I getting those numbers? It's the square of the natural numbers. 1 squared, 2 squared, 3 squared, 4 squared. Okay. Now, does this number show up in the list? Yes. So we can simplify it. Does this number show up in the list? No. But does it have any factors that show up in the list? 6 is not a perfect square. So it does have one number that shows up in the list, 4. So if I were to split root 24, I could split it into the square root of 4 times the square root of 6. I split it into perfect squares and non-perfect squares. Can I simplify either of those? Yeah, the perfect square becomes a 2, and I get 2 square root of 6. So all we're doing is removing the perfect square portion of these numbers. So let's look at 216. Do any of these numbers show up in 216? 4 does, and look at the factors. It's really easy to tell. Which factors did we remove? We removed a set of 2's, and we removed a set of 3's. So which perfect squares show up in 216? 4 and 9, and 4 times 9 would be 36. And notice 36 is also in the list. So 216 is the square root of 36 times the square root of what's left over? 6. And this becomes 6 root 6. So when you simplify square roots, all you're doing is taking the square roots of those factors that have perfect squares, which is why we need 2 numbers in a set. We're factoring out the 2 times 2 and the 3 times 3. If we were to look at the square root of 288, What's the biggest perfect square that you can see inside of 288? Here's a hint, divide it by 2. What's 288 divided by 2? 144. Is that a perfect square? So if we split this into the square root of 144 times the square root, what's left? 2. This becomes 12, and we have 12 root 2 is our answer. Because we have taken all of those perfect squares, so a 12 is 2, 2 times 2 times 3. So I had 2 pairs of 2s and 1 pair of 3s, and I pulled them out, and the leftover was a 2. Let's look at part D. What do I know goes into D? 5 does. What else? If we add the digits, we get 3 works. Well, what goes into something that ends in a 25? 25 will go into it, and if 25 and 3 go into it, then 75 must. So there are lots of ways to do this. So 25 and I think it's 245. So we factor this down, 5 and 5, 3 and 49, 7 and 7. What are we going to pull out? A set of 5s and a set of 7s. So what are my 2 perfect squares? Oh, is that 3 of 5? I'm sorry. So 3 didn't work, did it? So what is my perfect square there? So I'm pulling out a 25. What's my perfect square there? I'm pulling out a 49. And the square root of 25 is 5. And the square root of 49 is 7. If I pull out a 5 and a 7, I get a 35. With what left on the inside? A 5. How many A's can I pull out? How many sets of A's? One set with 1 left over. So A on the outside, A on the inside. Does anybody not understand how we're doing that? So we have A to the third, and we're pulling out groups of 2. So if I have all 3 of my A's, how many groups of 2 do I have? Just 1 group, and I still have a leftover A. So on the outside, I write how many groups there are, A to the first, 1 full group. On the inside, I write how many A's are left over, A to the first. So if we look at B to the 5th, I can write these down, B times B times B, B times B. How many groups of 2 are there? 2 groups. So on the outside, I write B squared because I had 2 groups. And I have 1 left over, so that leftover goes on the inside. Does that help? All right, if I have 10 C's, how many groups of 2 do I have? 5 full groups. How many leftovers will there be? So I count off my group 1, group 2, group 3, group 4, and group 5. None. I have no C's left over. So 5 full groups, nothing left on the inside. That would be my answer. And again, that might look more complicated than the original, but later on, it will make us capable of simplifying even further. We're just kind of practicing the rules today. Look at part E. Something's different about part E. It's a cubed root. We're no longer looking for groups of 2. We're looking for groups of 3. For every group of 3, we can bring 1 to the outside. We're looking for the perfect cubes. Instead of 4, 9, 16, 25, we're looking for 2 cubed, which is 18 or 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. So if I factor this out, do I have a group of 3? Yes. With how many left over? None. So I write 3 cubed root, what's left? So I take the whole group and I pull it out. And for every group, I'm allowed to write 1 on the outside. What's left? Nothing. And nothing is not 0, 1. Wait a minute. I thought 0 was nothing. In addition, 0 is nothing. In multiplication, 1 is nothing. Because 1 times a number is that number. All right. Am I going to have an I in part F? No I in F. It's a cubed root. The only time you have i's is when the root is even. So the number I pull out is going to be negative. So negative, help me out here, 8. I know 8 goes into it. 54, 8 and 54. 4 and 2, 6, 9, 2 and 2, 3 and 2, 3 and 3. And sometimes on a big list like this, it helps if you cross out the ones that factored. Do I have any groups of 3? I have a set of 2's, and I have a set of 3's. So what can I bring out? Close. Negative 6. So negative 6. What number gets left? 2. There's a 2 right here that wasn't used. So now if I'm looking for groups of 3, how many sets of 3 A's do I have? 1 set with how many left over? None left over. How many sets of B? 1 set. How many left over? So B squared on the inside. How many sets of C's do I have? 3 sets. C to the third. How many left over? Just 1. C. All right. Let's quickly do G and H. Now I'm looking for sets of 4. I know that 3 and 5 go into it, so 15. What is it? 81. 5 and 3. 9 and 9. Oh, sorry, that's a 3 and that's a 3. Do I have any quadruples? Yes. If this were a negative number, would I need an I? Yes, because it's an even root. Anytime you have an even root, you need i's. So, 3, 4th root, my leftover is 15. Those are the unused numbers. Do I have any groups of A? No, so I leave it in. A to the third. Do I have any groups of B? 2 groups. How many left over? B squared, nothing left over. How many groups of C do I have? 3 full groups. So C to the third. How many left over? Oops, C. Just 1 C left over. Are we getting the hang of this? Okay. Letter H. If this were negative, would I need an I? No. If it's an odd root, you do not need an I. I know this is 10 and 32, 5 and 2, 4 and 8, 2 and 2. Oh, sorry. There's another 2 there. Do I have any quintuples? Yep, right here. So I can pull out a 2, and I'm leaving in a 10. This is a fifth root. I don't have enough x's, so the x's remain inside. I have enough for one group of y with nothing left over, and I have enough for 2 groups of z. How many z's would I have left over? 2 left over. So your assignment tonight is to finish this worksheet. The answers are on the back. You need to show your work. Good luck.